Number 20, which molecule has the largest dipole? Now, a dipole is a delta plus and a delta minus. That occurs when you get an electronegative atom withdrawing electrons along a bond towards itself. Now, electronegative atoms, the three most electronegative atoms are F, N, and O. They're very electronegative atoms, and F is in them all. So that's going to withdraw electrons towards itself and create a delta minus and leave either the Cl, the B, the S, or the C with the delta plus. The question is, which is it going to withdraw electrons the most from? That's the question. So F withdraws electrons towards itself because it's electronegative. The other ones get electrons withdrawn away from them. They're actually called electropositive. So which one gets the electrons withdrawn away from the most? And the simple answer is it's the atom with the most electrons. If it's got more electrons, it's got more to withdraw. So the answer is A, because Cl is the biggest atom with the most electrons. So that's got the most electrons to withdraw, so that would create the biggest dipole, delta plus, delta minus. It's as simple as that. In a molecule of a hydrocarbon, the fraction mass of carbon in there is 9 to 11. Which is it? So what you've got to do is the fraction, you've got 9 parts carbon to 11 parts in total. So what I do is I work out the mass of the carbon in there, again divide it by the mass of the overall MR, and whichever one is 9 divided by 11 is the answer. So here the carbon is 12, a hydrogen is 1, so it's 12 divided by 12 add 1 is 13, 12 divided by 13. I've got CH3, so I've got a 12 and 3 1s. 12 add 3 1s is 15. I've got 12 15ths is carbon. I've got C3H6, so 3 carbons are 12, add 6 hydrogens, 3 carbons 12 each is 36, add 6 hydrogens, 36 add 6 is 44. I've got 36 divided by 44, that's 9 divided by 11. If I divide top and bottom by 3, 9 divided by 11, 36 divided by 44. Sorry, if I divide top and bottom by 4, 36 divided by 4 is 9, 44 divided by 4 is 11, it's 9 11ths. And then I've got C5H12, 5 12s are C5H12, I've got 5 12s are 60, add 12 for the hydrogens, 72, so 60 for the 5 carbons, add 12 for the hydrogens, 60 add 12 is 72, that's not 9 11, the answer is C. AS Paper 1, May 2016. I've just got a periodic table here with the atomic numbers or the proton numbers of each of the elements to help us in the next question. Give the full electronic configuration of an Al atom. So let's have a look what an Al atom is. It's got 13 electrons. So it's going to have 1s2, 2s2, 2p6, 3s2, 3p1. 2 add 2 is 4, add 6 is 10, add 2 is 12, add 1 is 13. So that's how they fit into shells and subshells. Cr3+, so let's have a look at Cr3+. So chromium has got 24 electrons. So if it's 3+, it will have 21 electrons. If it had 24 electrons, it would have 3d4 and then 4s2, but it loses the 4s2 before it loses any 3ds. So it loses 4s2 first, and then it loses one of 3d to make a 3+ ion. So it's gone down from 24 to 21 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. 2 add 2 is 4, add 6 is 10, add 2 is 12, add 6 is 18, add 3 is 21. So it's had 24 electrons, 3+ lost 3 electrons, gone down to 21 electrons, and the 3 that have been lost have come from the 4s2 first, and then one of them from the 3d to make 3d4 go down to 3d3. Deduce the formula of an ion as a 2+ charge with the same electronic configuration as krypton. So let's find krypton. Krypton has got 36 electrons. So I'm looking for something that ends up with 36 electrons. It's got a 2+ charge, this element, so it's had 38 electrons and lost 2 to have 36 electrons, the same as krypton. So something with 38 would be 38 electrons. We're looking for SR. We're looking for strontium, 38 electrons. If it becomes 2+, it goes down to 36 electrons, krypton. So it's an SR atom that's lost 2 electrons. It's SR2+. Deduce the formula of a compound that contains 2+ ions and 3- ions, both of which have the same electronic configuration as argon. So we're looking for a 2+ and a 3- ion that have got the same electronic configuration as argon. So let's have a look at argon. Argon's 18. So a 3+ is a P, which is 15, because 3- means it's gained 3 electrons and become 18. So P3- has gone from 15, 3- gained 3 electrons up to 18. And calcium 2+, 20 to start off with, 2+ lost 2 electrons to go down to 18. So P3- has 18 electrons, gained 3 electrons and gone from 15 to 18. Ca2+ has lost 2 electrons and gone down from 20 to 18. So I've got P3- and Ca2+. So what's its formula? Well, calcium is 2+, P is 3-, so 3 2+ make 6 pluses. 2 3- make 6- to leave no charge left over. So we end up with Ca3, Ca2+, we've got 3 of those, and P3-, we've got 2 of those, 6+ and 6- leave no charge overall. Question 2. This question is about period 3 of the periodic table. So in period 3, they've all got 3 electron shells. All the atoms have got 3 electron shells. So they've got the same number of shells, therefore shielding doesn't come into it. Deduce which of Na1+ and Mg2+ is the smaller ion. Well, let's go back to our periodic table. So Na is here with 11 electrons and 11 protons. If it loses 1 electron and becomes Na+, it loses 11 electrons. 1 is lost and it becomes 10. So Na1+ loses 1 of those 11 electrons and it gets 10 electrons. Still got the 11 protons, just gets 10 electrons. Mg2+, 12 protons and 12 electrons. If it becomes Mg2+, it loses 2 electrons and gets 10 electrons. In other words, they both can have the same number of electrons. Na1+ loses 1 electron to become 10 electrons. Mg2+ loses 2 electrons to become 10 electrons. They've both got the same number of shells, 3 shells, same amount of shielding. The only difference is Mg has got 12 protons still. Remember, protons are unaffected when it becomes an Mg2+. And Na has got 11 protons, still got 11 protons when it becomes an Na+. So, which one's going to have the greater nuclear charge? Mg's got 12 protons, greater nuclear charge, greater nuclear attraction for the electrons that it has, same number of electrons, same amount of shielding, greater nuclear attraction. That Mg2+ is going to be smaller than Na+. Write an equation to represent the process that occurs when the first ionization energy for sodium is measured. Remember, ionization energies, the atoms are as gases, so Na is a gas. First ionization energy is the first electron removed, so it hasn't got any electrons removed here. It becomes Na1+, because it's had 1 electron removed, first ionization energy, still a gas, and the electron is shown as being removed as an E-. The first ionization energy of some period 3 elements are shown in figure 1. So we've got sodium, magnesium, aluminium, silicon, phosphorus. Sulphur isn't shown. We've got chlorine and argon. In theory, they should all go up. So they should go up and each should increase. There's a couple of blips in there, and we'll talk about a couple of blips, but they should all go up because they've got the same number of shells, 3 shells, same amount of shielding. It's just every time you go across the period, you get one more proton, increased nuclear charge, increased nuclear attraction, greater attraction for the electrons, and therefore the ionization energy increases. The energy to remove those electrons increases due to the greater number of protons and the nuclear charge. So this goes up, so it's going to go up somewhere here. Interest in magnesium comes down, and we'll talk about that in a minute, but it goes up. So we're looking at magnesium coming up somewhere here because it's got 12 electrons rather than 11 electrons. Magnesium's got more electrons than sodium, so it's got a greater nuclear charge, and therefore it's going to require more energy to remove that electron. In this sort of region here, interestingly, it's higher than aluminium. Aluminium comes down because this has got 3 s2 electrons, this has got a 3p1 electron. So s2 electrons, 3 s2 electrons are more difficult to remove than a 3p1 electron. So a 3p1 electron is more easily removed. And so magnesium comes down here. Let's have a look at sulphur then. Sulphur is in this region. It comes down. The reason that sulphur comes down is that this has got 3p3. So phosphorus has got 3p3. Magnesium, aluminium 3p1. Silicon 3p2. 3p3. The 3p3, it's half full, and the 3 electrons are not paired. In sulphur, you've got 3p4, so you've got 3 single p electrons, and you've got a pair, so 3 single p electrons, and the 4th electron pairs up with one of those 3p electrons. So you've got a pair of electrons, and they start to repel. So that 4th electron, it has to pair up with one of the other 3 single 3p electrons, and that pair repels, and that's why it's easier to remove the 4th p electron from sulphur than it is from phosphorus that's got 3 unpaired p electrons. Question 3. We've got a white solid, MHCO3, so we don't know what this is. It looks as if it's fictitious. There's no such symbol, atomic symbol as M. There's no element such as M, so it's made up. Okay. Student has designed an experiment to determine the value of the MR of MHCO3. The student dissolved 1,464 milligrams. So we might have to convert that into grams by dividing by 1,000 at some point, I'm thinking, of MHCO3 in water, made the solution up to 250 centimetre cubed. A 25 centimetre cubed sample, oh that's important, they've taken a 10th of the liquid, so 25 centimetre cubed out of the 250, they've taken a 10th of the amount. We might have to multiply up by 10 at the end. Samples of the solution were titrated with 0.102 mole per decimetre cubed of hydrochloric acid. The results are shown below. Okay, so these are volumes of hydrochloric acid. We've got 4 titrations, a rough and 3 others. Calculate the mean titer and use this to determine the amount of moles of HCl are needed to react with the 25 centimetre cubed of the MHCO3 solution. Okay, first of all, let's have a look at the titers. So it's what they start off with on the initial reading on the burette, the final reading on the burette, and they've subtracted the two to give the amount of hydrochloric acid that's been added. In the rough titer, 10 centimetres cubed, 10.00, 9.5 on the second one, 9.75 on the first one, 9.75 on the second one, and 9.65 on the third one. Now we need to decide which ones do we use and which ones to ignore. We use any two that are within 0.10 centimetre cubed of each other. So 9.50 and 9.75 are 0.25 apart. They're too far apart. 10 is way out, so we won't use the rough one. 9.50 and 9.65 are 0.15 centimetre cubed apart, so just outside the 0.1 range. So it looks as if we're not going to use the rough one at all. That's way out, and the titration 1 is over 0.10 centimeters cubed away from titrations 2 and 3. We hope that titrations 2 and 3 are within 0.10 centimeters cubed of each other, and yes they are. If you take away 9.75, take away 9.65, it's 0.10. So these two are the two to use. We call those concordant results. Concordant means the two values are within or less than, equal to or less than 0.10 centimeter cubed apart. So we're using titrations 2 and 3. So we add the two together, divide by 2, 9.70 is the mean titration. Look, I'm doing it to 3 significant figures because all of the other 3 titrations, 1, 2 and 3, are to 3 significant figures as well. Now then, calculate the mean titer and use this to determine the number of moles of HCl. Okay, so I've got the volume, I've got a concentration of HCl, I've got concentration of HCl, so concentration is moles divided by volume. My volume is 9.7. I've got to get it into decimeter cubed first of all, so volume is going to be in decimeter cubed. So 9.7 centimeters cubed up into a higher value of decimeter cubed, I divide by 1000, 0.0097 decimeter cubed. Now concentration is 0.102 for hydrochloric acid. It tells you that in the question, equals moles divided by 0.0097. That's the volume in decimeter cubed. Multiply the two together, 0.0000989 are the number of moles. And I've got it still to 3 significant figures. So now I've got the number of moles of HCl that react with the MHCO3. Calculate the amount in moles of MCH3 in the 250 centimeters cubed solution. Well, the number of moles of HCl that react with the number of moles of MHCO3, 1 mole of HCl reacts with 1 mole of MHCO3. So this number of moles, 0.000989, will also react with the same number, 0.000989 moles of MHCO3. So I've got the number of moles of MHCO3 as well, which equals this. But it's in the 25 centimeter cube sample, so I need to scale it up to what would be in the 250 original volume. So I do 250 divided by 25 is 10, and multiply by 10. I've got to multiply up by 10. So I take this value and I multiply it up by 10. So now I've got 0.00989 moles in the 250 centimeters cubed. What else do I know? Well, I know that I've got 1464 milligrams of the MHCO3 in there. I convert that into grams by dividing by 1000. Remember, a small unit value into a bigger unit value, you divide by 1000. I've got 1.464 grams, and now I can use moles, is mass in grams divided by MR. I don't know the MR, but I do know the moles and I do know the mass. So the MR is 1.464 divided by 0.00989 is 147. I've got it to 3 significant figures because the other measurements are 3 significant figures as well. The student identified the use of the burette as the largest source of uncertainty in the experiment. Using the same apparatus, suggest how the procedure could be improved to reduce the percentage uncertainty in the burette. So you've got an uncertainty on a burette, and to get the error you divide the uncertainty by the volume that's coming out of the burette. So in here I've got 9.75, 9.65, so whatever the error is on my burette, whatever my uncertainty is on my burette, I take that uncertainty value and divide by the volume, which turns out to be 9.7 as a mean value, and multiply by 100. Now if I'm dividing by a number, the larger this number is that I divide by, the smaller the error. So let's say, I don't know, the uncertainty on a burette was 1 centimeter cubed. It's 1 divided by 9.70 multiplied by 100. If I made that 50, it would be 1 divided by 50 multiplied by 100. I've suddenly reduced the percentage error, made it smaller by making this volume larger, so that my uncertainty divided by the volume, if the volume is larger, this uncertainty divided by this larger volume multiplied by 100% gives a smaller percentage error. In other words, I'm looking for a larger value coming out of my burette. Now, if I'm going to keep everything the same, number of moles and etc., but I want a larger volume coming out than my burette, I need the liquid, the solution, to be more dilute. So I'm going to use a more dilute solution of HCl, and that will give a bigger reading on the burette, so a larger titration reading will be needed. That will give me a lower percentage error. Okay, another student is required to make up 250 centimeters cubed of an aqueous solution that contains a known mass of MHCO3. The student is provided with a sample bottle containing this solid. Describe the method using the apparatus and the practical details that the student should use to prepare the solution. So I've got to try and get a known amount of this solid into 250 centimeters cubed in something like a volumetric flask. A volumetric flask is a flask with a mark on it, and that mark, when you fill it up to the bottom of the meniscus on that mark, it means you've got 250 centimeters cubed of solution in there. So first of all, I've got to get the solid out of the sample bottle. I've not got to get it all out of the sample bottle. I've just got to know how much has come out of the sample bottle, because it says I've got to have a known mass. So as long as I know how much I've taken from the sample bottle, that's okay. So what I'm going to do is I'm going to put a beaker onto a balance. I'm going to press the tare button. The tare button zeroes the balance, so it imagines that the beaker isn't there. And I tip the solid into the beaker, and I record the mass on the balance. I could have measured the mass of the beaker beforehand and measured the mass of the solid in the beaker and taken it away, but I think it's just easier to say press the tare button on the balance, and then it ignores the mass of the beaker that you're pouring it into. Now then, I've got the solid in the beaker and I've got to get into the volumetric flask. So how am I going to get a solid into the volumetric flask? Well, first of all, I can dissolve it in a little bit of water. That'll make it easier to pour then into the volumetric flask. So I'm going to add some distilled water. Use distilled water because it's got no impurities in it. Stir it, swirl it to try and dissolve the solid. And then you can tip it into the volumetric flask and then wash out any remainder. So pour that solution then into the volumetric flask, wash it out, so wash out the beaker, pour a little bit more in, wash out the beaker, pour a little bit more in, until all of the solid has been removed from the beaker, and any little bits and things have been washed out of the beaker into the volumetric flask. And then you make it up, you pour more of the add more distilled water until it comes up to the 250 centimeter cubed mark on the volumetric flask. Question 4. We've got some data about elements bromine and magnesium. We've got melting points and boiling points. Explain in terms of structure and bonding why the boiling point of bromine is different from that of magnesium. If we have a look at it, it's a lot lower, so bromine's a lot lower in terms of melting point and boiling point. And in terms of the difference, we've got a sort of difference of about 66 degrees here, and we've got a much larger difference of over 400 degrees here. So that's something else to note, that there's differences between the melting point and boiling point. Magnesium, it sort of stays a liquid for a lot longer, over a longer temperature range, over a larger temperature range before it starts to boil. So let's have a look then. Bromine is, first of all, bromine is Br2. So what bromine does, Br2, Br atom is in group 7 of the periodic table, wants to gain an electron. So they pair up in twos, Br2. They each put an electron in each into the covalent bond and fill their outer shell. So Br2 with a covalent bond between two Br atoms. And then each Br, so it's molecular. Molecular means that it's just a small number of atoms covalently bonded together. So Br2 is just two atoms covalently bonded together. Now, that's going to have a very low boiling point and a low melting point, because there's no electronegativity, so there's no polar bonds, no dipole-dipole attractions, there's no hydrogen bonds, there's no oxygen bonded to a hydrogen, or nitrogen bonded to a hydrogen, or fluorine bonded to a hydrogen. So it's just van der Waals forces which are weak, and that is why it's got a low boiling point. Magnesium, incidentally, magnesium is a metal, so it's got metallic bonding. So what that means is the atoms lose electrons and form plus ions, and the electrons are delocalized. They move between the metal. It's also a reason why it conducts electricity, the moving electrons. But the moving electrons then are delocalized, and the ions, the plus magnesium ions, bond to the minus delocalized electrons which are moving through the metal, and that's called metallic bonding. It's quite strong, actually, metallic bonding. Not as strong as something like ionic bonding, but it's quite strong. So it's going to have a relatively high melting point and boiling point. So Br has weak van der Waals forces between the molecules, so more energy is needed to overcome the stronger metallic bond. So you could say that less energy is needed to overcome the van der Waals bonds than the metallic bonds. And finally here, the magnesium for the 5th mark is to talk about this range. So magnesium has a greater range. It's a liquid for a longer temperature range. See, it's a liquid when it melts and then starts to boil. That's a large temperature range. It's a liquid for a long time over a large range of temperatures, and that's because in the liquid metal the force of attraction and metallic bonds are still strong. They're strong in a liquid metal. Question 5. Figure 2 represents two glass flasks P and Q. P looks a bit smaller than Q, connected via a tap in the middle. Flask Q, volume 1 times 10 to the power 3 centimetre cubed, is filled with ammonia. So Q is filled with ammonia, which is NH3, 102 kilopascals and 300 degrees Kelvin. The tap is closed and there's a vacuum, means that there's nothing in flask P. The gas constant R is 8.31. That gas constant R gives you a clue straight away, and we're talking about gases anyway. PV equals nRT is the gas equation, and that's the gas constant. So I'm going to use PV equals nRT. So PV equals nRT, what do? P is pressure. Pressure, 102 kilopascals. It needs to be in pascals. Kilopascals into a smaller unit value like pascals and multiply by 1,000. So 102 kilopascals down into pascals, which is a smaller unit value, and multiplying by 1,000. 102,000 pascals. So I've got the pressure in the right units. V is volume. So volume. So what's my volume? My volume is in centimetres cubed. It needs to be in meters cubed. Now, centimetre cubed going up a unit value goes up to decimetre cubed, and then decimetre cubed goes up to meters cubed. So in between centimetres cubed and meters cubed, there's another unit value of decimetre cubed. So if I'm going from a small unit value up to a large unit value, then I divide by 1,000. So it's 1 times 10 to the power of 3, which is 1,000 centimetre cubed. Up into decimetre cubed is divided by 1,000, and then divided by 1,000 again to get decimetre cubed into meters cubed. So it's 1 times 10 to the power of 3, which is 1,000, divided by 1,000, then divided by 1,000 again. So it's 0.001 meters cubed. That's my volume now. N I don't know. I think that's what I've got to find out. Find out the mass of ammonia. Well, I can find out, if I find out N, the number of moles, I can probably find out the mass from that, especially if I know the MR of NH3. R is the gas constant, I've got that. T is the temperature in Kelvin. It's already in Kelvin. If it was in degrees C, I'd have to add on 273 to get it into Kelvin, but it's already in Kelvin, so that's 300. So I'm just starting to put these in now. 102,000 pascals multiplied by 0.001, that's my volume in meters cubed, equals N, the number of moles, multiplied by 8.31, which is my gas constant, multiplied by 300, which is my temperature in Kelvin. So N is 102 divided by 8.31, because I'm taking it across the other side, divided by 300. N is 0.041, that's the number of moles. Now I'm given the formula of ammonia. I wonder why I've been given the formula, probably so I can work out MR, because I've got number of moles is mass divided by MR, and I've got the number of moles, I've just worked that out, it's 0.041. If I can work out the MR, a nitrogen's a 14 and a hydrogen's 1, I've got 3 hydrogens, so I've got 14, add 3 ones, 17. So number of moles 0.041 is mass divided by the MR, 17. Mass is 0.041 multiplied by 17. My mass is 0.696. Now, how many significant figures? Everything. 1.00 is 3 significant figures. 8.31, 3 significant figures. 102, 300. They're all to 3 significant figures. So let's get to 3 significant figures. 0.696 grams. Okay. The next part of the question. When the tap is opened, ammonia passes into flask P. So it's going from here through the tap into flask P. So I've now just increased the volume. The temperature decreases by 5 degrees C. So now instead of the temperature being 300 Kelvin, it's now, if I decrease by 5 degrees C, every time I come down by a degree C, I come down by 1 Kelvin. So every time I go up by a certain number of degrees C, and I go down by a certain number of degrees C, the number of Kelvin changes by the same amount. The only difference is that to turn degrees C into Kelvin, you need to add on 273. Okay, so my new temperature is 295 Kelvin. The final pressure is 75.0 kilopascals. To get that into pascals, remember, I would multiply by 1,000, so that's 75,000 pascals. Calculate the volume in centimetre cubed of flask P. Well, I can calculate the whole volume, so PV equals nRT. Pressure is 75,000 pascals, so I've taken the 75,000 kilopascals, multiplied by 1,000 to get a large unit value down into a smaller unit value. Number of moles isn't changed. All I've done is just open the tap and made new space, new volume available. I've not changed the number of moles of ammonia at all. So that's exactly the same, 0.041. Temperature I've said has come down by 5 degrees C, which is the same as coming down by 5 Kelvin, 295. So now I can start putting these numbers in. 75,000 pascals multiplied by the new volume. I don't know what the new volume is. I think that's what I'm trying to calculate. N is the number of moles, 0.041, which is the number of moles of ammonia, which is unchanged, 8.31. The gas constant's unchanged, and 295. All of that, 0.041 multiplied by 8.31 multiplied by 295 equals 100.51. So 75,000 times volume equals 100.51. So 100.51 divided by 75,000 equals 0.00134. And it's in meters cubed. Remember, volume in this equation is in meters cubed. Now I can convert it into decimeter cubed and convert it into centimeters cubed if I want to get a unit value from a large unit value in meters cubed down to a smaller one, decimeter cubed, I'd divide by 1,000 to get decimeter cubed down into the next smaller one, centimeters cubed, I'd divide by 1,000 again. So that's the total volume of both flasks. So both of them together. Do I know the volume of flask Q? Yes, I've been told that in the question. I worked it out earlier. Is 0.001. So if I subtract the that's the volume of the whole flask, 0.00134. Subtract 0.001, which is the volume of flask Q. I'll end up with the volume of just flask P on its own, 0.00034 meters cubed. If I divide by 1,000, sorry, if I multiply by 1,000 to get meters cubed into decimeter cubed, so multiply by 1,000, it would be 0.34 decimeter cubed, multiplied by 1,000 again to get into centimeter cubed, 340 centimeter cubed. So when I take a large unit value down into a smaller one like decimeter cubed and multiply by 1,000 and then multiply by 1,000 again to get the decimeter cubed down into centimeter cubed, 340. Question 6.1. Explain how ions are accelerated, detected and have their abundance determined in a time of flight and mass spectrometer. Well, let's explain all this first of all. So you introduce gaseous particles into this time of flight mass spectrometer. Now at the moment they've not got any charge on them, so what you do is you bombard them with something called high energy electrons. You do that with the use of something called an electron gun, which is a hot wire. The hot wire releases electrons, high energy electrons. Then they bounce into the particles, they collide with the particles and knock further electrons off. So the particles, now the gaseous particles, have an electron removed and they end up with a plus charge. Now you've got ions, atoms that have got a plus charge now, so particles with a plus charge because they've had electrons removed by bombarding them with other high energy electrons. Now you've got positively charged particles. They can be accelerated. They're accelerated towards plates with holes in them, and the plates are charged minus, so they're negatively charged plates, and the plus charged ions, they're atoms that have had electrons removed, and electron removed form a plus ion. These plus ions, because they've been particles, atoms that have had an electron removed by these high energy electrons being bombarded into them, these plus ions then get accelerated towards some plates that are negatively charged. So positive ions get attracted to the negatively charged plates. They go through the holes, because the plates have got holes in them, and they hit something called a detector plate. When they hit a detector plate, the plus charged ions accept an electron from the detector plate. And in accepting an electron from the detector plate, that makes a current, and we can measure the current. It makes an electrical current. So the plus charged ions turn back into atoms by accepting electrons and creating a current, an electrical current. Depending on the size of that electrical current, we know how many there are. Abundance means how common they are, how many there are. So the ions are attracted to negatively charged plates. The ions detected by gaining electrons from the plate. So when they hit the plate, the plus charged ions get their electron back and turn back into atoms, and their abundance, their amount of them, is found out by the size, the current that's detected on the plate, or the number of electrons gained on the detector, that is. So when they hit the detector, positively charged ions get their electron back, and depending on how many hit the detector plate, then we can detect the current flowing, and that tells us how many have hit the detector plate. Calculate the mass in kilograms of a single 52 chromium plus ion. So the chromium plus ion has had an electron removed, and it's going to accelerate down this plate, hit the detector, and then the plus ion will gain an electron, make a current on the plate, and we can work out, depending on how many electrons or what kind of current, the size of the current, when these hit the plate, we can work out how many of these are hitting the plate. Assume the mass of 52 chromium ion is the same as a 53 chromium atom. It's only had one electron removed and becoming plus, and electron mass is negligible, next to nothing, so that's fine. So 52 chromium, so 1 mole is 52 grams. So that's what the 52 is. So 52 grams of chromium is got a mass is 1 mole. So 1 mole, to get it into kilograms, it wants it in kilograms. To turn grams up into a high unit value of kilograms, I divide by 1,000. 52 divided by 1,000, 0.052 kilograms. Now I want the mass of one of these particles. So I know Avogadro's number is the number of particles in a mole. So 52 grams of this, or 0.052 kilograms of this, of our 52 chromium ion, contains 6.022 times 10 to the power of 23 particles, Avogadro's constant, Avogadro's number. So if that's the number of that's the mass of 1 mole, and 1 mole contains that number of particles, if I divide 0.052 kilograms by 6.022 times 10 to the power of 22, I find the mass of one particle in kilograms, 8.6 times 10 to the minus 26. In a time of flight mass spectrometer, the kinetic energy of a 52 chromium ion was 1.269 times 10 to the minus 13. So now I've got the kinetic energy, and it also gives me this equation. Kinetic energy is half mv squared, where m is the mass of one particle in kilograms. So I've now got the m as well. So let's get rid of the half first of all. Let's multiply both sides by 2, and that'll get rid of the half. So 2 times 1.269 times 10 to the minus 13 equals just mv squared. The mass is the mass of a particle, which got me to work out before, 8.6 times 10 to the minus 26. So 2 times 1.269 times 10 to the minus 13 equals 8.6 times 10 to the minus 26 times v squared. Divide 2 times 1.269 times 10 to the minus 13 by 8.6 times 10 to the power of 26. That equals v squared. I square root it at 1.71 times 10 to the power of 6. And it's in meters per second. Bromine has 2 isotopes, in approximately equal amounts. In a time flight mass spectrometer, it forms ions Br2+. In other words, a Br and a Br have joined together. Yes, they become plus charged, so they've lost an electron. That's not going to change the mass. It's only going to be a negligible change in mass. An electron being removed, an electron has negligible, next to no mass. So what combinations could we have? Well, we've got the 2 isotopes. We've got 79 and 81, 79 Br and 81, and they're in equal abundance. That means they're in equal amounts. So what combinations could I have? I could have 2 79 Br atoms coming together. I could have 2 81 Br atoms coming together. I could have a 79 Br atom combining with an 81. So this one's on the left and this one's on the right, and they'll join together. Or I could have the 81 on the left and the 79 on the right, so I could have that combination as well. So I've got 25% of each of these combinations. So 25% of 79 two 79s, I've got Br2, two 79s will be 158, so a Br2 with two 79 atoms in there, I've got a mass of 158, and I've got 25% of that. I've got two 81 atoms, so combined Br2, 162, 25% of that. I could have a 79 atom joining with an 81. 79 add 81 is 160, and I've got 25% of that. Or I could have them the other way around, an 81 joining with a 79 to give a mass of 160, 25% of that. So I've got 25% is 158, that's two 79 Br atoms coming together. I've got 50% is 160, that's a 79 atom coming together with an 81 atom, or an 81 atom coming together with a 79, so I've got 25% of each, 70, so both have the same mass, 160, so I've got 50% of that, and then I've got 25% of two Br 81 atoms coming together at 162. Okay, a sample of xenon. Mass 131.1, so that's the average. So when I work out the average from all of these different isotopes, the sample consists of 4 isotopes. The abundance of 3 isotopes are shown in table 3. The data for one of the isotopes is missing, so I've got to calculate what the percentage abundance is for this. So I know that the average of all 4 of them equal this. So when I've got percentages, I always imagine, I think it's easier to imagine that I've got 100 particles in my sample. Why not? I've got 100 particles in my sample. So for this isotope I've got 28 particles, for this isotope I've got 25 particles, for this isotope I've got 27 particles, and then I've got a certain number of particles of this. So I work out the number of particles of this that I've got. That's what I've got to try and work out. So my abundance is 100, so this one, the abundance, the percentage abundance is 100, take away 28, take away 25, take away 27, I've got 20% of this. So 28% is this one, 25% is this one, 27% of this one, and by subtraction the remaining percentage must be 20%. So all of these add up to 100%. So I don't know what mass this is. That's what I'm trying to find out, the mass of this xenon particle. Its mass number, and I don't know. So let's give it a letter. Let's give it the letter M. I'm imagining that I've got 100 particles. So what mass are 129 xenon? Well, I've got 28 out of the 100 particles. Out of 100%, or 100 particles, 28 of them have got a mass 129. So their total mass is 28 multiplied by 129. So those particles, I've got 28 particles, mass 129, so 28 times 129 tells me the total mass of these particles. I've got 25 particles, mass 131, so if I multiply 25 by 131, it'll give me the mass of all of these particles. I've got 27 particles, mass 132, if I multiply 27 particles, each of them mass 132 together, it will give me the mass of all of these particles. I don't know the mass of these particles, but I know that I've got 20 of them, so 20 multiplied by the mass, which we're calling m, which we don't know, is 20 times m. Now all of these total masses added together is the total mass of all of the 100 particles. If I divide by the number of 100 particles, which is 100, divide by 100, then it'll give me a value, an average value, except that it won't quite because I've got m. So what I'll do is, I tell you what, I'll take the divide by 100, I'll take it across the other side, and I'll multiply the 131.41, which is the average, the mass of all of the particles all together divided by 100. I'll multiply this by 100, so 13141 equals this value, 28 times 129, which is 3612. 25 times 131 is this value, 3275. 27 times 133 is 3591. 20m is just 20m. And I'll take all of these numbers across to the other side and subtract them from 13141. 141. So 13141. Take away 3612. Take away 3275. Take away 3291 equals 20m, and 2663 equals 20n. So divide both sides by 20 to leave m. M is 134. Now it's got to be a whole number because these mass numbers must be whole numbers, because that is the mass of, that's the number of protons plus neutrons in an atom. The mass number, the protons and the neutrons have atomic masses of 1 each, and so they have mass within the atom, and you can't have odd numbers of protons and neutrons in an atom, so it's got to be a whole number. So I've rounded up to the nearest whole number. Ammonia reacts with aluminium chloride is shown by the following equation. So ammonia is NH3, aluminium chloride is AlCl3. Draw diagrams to the shapes of NH3 and of AlCl3 molecules. Well, nitrogen's in group 5 of the periodic table, so it's got 5 electrons around it. It's got 5 in its outer shell. So it's in group 5 electrons in the outer shell. 3 of those electrons will be bonded in bonded pairs with each of 3 hydrogens. So 3 are used in 3 bonding pairs, and there's a lone pair left over. Now, if there were 4 bonding pairs, it'd be tetrahedral. However, if there's 4 bonding pairs, it's tetrahedral, but one of them is now a lone pair. So we still sort of draw that on, the lone pair, but we know we don't see it, so we only include these 3 when we describe the shape. So it's pyramidal, or trigonal pyramidal. So it's a trigonal pyramid because it's got a base of 3. It's a trigonal pyramid. Now, if it were tetrahedral, 4 bonding pairs, something like CH4, say for example, then the bond angle would be 109.5. But when you replace one of the bonding pairs with a lone pair, the bond angle 109.5 comes down by 2.5 degrees. So 109.5 subtract 2.5 is 107. If there was another bonding pair replaced, so if one of these NHs was replaced with another lone pair, 107 would come down to 104.5. 107 take away 2.5 when you replace a bonding pair with a lone pair, brings it down to 104.5. So that would be something like water, incidentally. Anyway, it's a trigonal pyramid with a lone pair, 3 bonding pairs, bond angle 107. What happens in AlCl3? Well, that's slightly easier in actual fact. You've got 3 bonding pairs because aluminium's in group 3, so 3 electrons in its outermost shell. 3 chlorines bond those 3 electrons. Now, if there's 2 bonding pairs or 3 bonding pairs, then it's planar. So it's planar, and it's got a bond angle of 120, so it's trigonal planar. It's only when you get 4 bonding pairs, or when the number of lone pairs add up the number of bonding pairs, go above 3, so 1 lone pair add 3 bonding pairs, 1 add 3 equals 4, that it stops being planar. Up until then, if there's 2 bonding pairs or 3 bonding pairs, it stays as planar. Trigonal planar, bond angle 120. Name the type of bond formed between N and Al in this compound and explain how the bond is formed. Well, the reason that N can bond to something like Al is because it's got a pair of electrons. Al hasn't got any electrons, so Al can't put an electron into a covalent bond and nitrogen put an electron into a covalent bond, because aluminium, AlCl3, hasn't got any electrons in its outer shell. It's just bonded its 3 electrons that it had in its outer shell to 3 Cl, so it's got none left. So if it's going to bond to the N is going to have to put this pair of electrons into the covalent bond. So rather than the Al putting an electron in and the nitrogen putting an electron in and forming a covalent bond, they do form a covalent bond, but both electrons come from the N rather than one from the Al and one from the N. So if you get a covalent bond set up where both the electrons have come from one of the atoms rather than one electron coming from each of the atoms, that's called a dative bond or a covalent bond. So it's a dative or a covalent bond. They mean the same thing, they're just different words for the same thing. So coordinate bond or dative bond, both electrons come from the N. Explain how the value of Cl-AlCl bond changes. Well, suddenly you've got a 4th bond. So here you had 3 bonds. Now you've got a fourth bond. It's bonded to an N. It's bonded. This N has suddenly bonded. So now instead of 3 bonding pairs, you've got 4 bonding pairs. 4 bonding pairs changes. So the 4 bonding pairs, just like on something like 4 bonding pairs, it's larger than 3 bonding pairs, so it's not going to be planar. 4 bonding pairs is going to be something like tetrahedral. It's going to be tetrahedral like something like methane, CH4, 4 bonding pairs, and 4 bonding pairs have a bond angle of 109.5. Question 8. A student oxidized. So what's oxidation? Oxidation is loss of electrons. Okay, oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Oil rig. Okay, so something's being oxidized. It's losing electrons. Oxidation is loss of electrons. A solution of hydrochloric acid. So a student oxidized a solution of hydrochloric acid. So the hydrochloric acid is being oxidized. It's losing electrons. With a few drops of sodium chlorate 1 solution. Oh, we're going to have to work out what sodium chlorate 1 is. The reaction mixture F of S, that means it made a gas and turned pale green, a pale green gas. The gas formed bleach universal indicator paper. Now chlorine's a pale green gas and chlorine is used in bleach products, so maybe we're making chlorine gas. Write a half equation for the oxidation of chloride ions. Now a chloride ion is a chlorine atom that's gained an electron. Chlorine, Cl, is in group 7 of the periodic table. It wants to gain 1 electron, so it wants to form Cl minus ions and gain an electron. That's what a chloride ion is. Now if it's oxidized, oxidation is loss, so the Cl minus ion is losing an electron. So it looks a bit like this. That's a chloride ion, a Cl, a chlorine atom that's gained an electron, a chloride ion. Remember, an ion is a plus or a minus charged atom. An atom that's lost or gained electrons to fill up its outer shell. So this chloride ion is a chlorine atom that's gained an electron to fill up its outer shell. If it's been oxidized, it's lost its electron. There it is, the electron's lost, and it's lost the minus charge. So it had a minus charge, which means it gained an electron. Now the electrons come off and it's lost its minus charge. It's just become Cl. Don't be afraid, by the way, a half equation involves electrons. It's got to involve electrons. If you don't involve electrons, if you don't see any E minuses in a half equation, you've got it wrong. The one thing that's not quite right about this is that chlorine atoms, if you make chlorine atoms, they tend to pair up in twos, because as we were saying, chlorine is in group 7 of the periodic table. So 2 Cl's can come together and each put an electron into a covalent bond, into a pair. So between 2 Cl atoms, Cl2 will form between 2 Cl atoms, where each atom puts an electron into a pair and form a covalent bond. So we know Cl is going to form Cl2. The issue then is that it doesn't balance. 2 Cl's, Cl2, 2 Cl's, I'll need 2 Cl minuses, and now I've made 2 minuses on the left, so I need 2 electrons being released on the right hand side. So 2 minuses on the left, 2 minuses on the right. And that's oxidation. Because it's a half equation, because there's electrons in there. It's oxidation because something, the Cl minus, has lost electrons. The other way of looking at oxidation is it's a -1 ion. It's in oxidation state -1. Cl on its own, Cl2 on its own, is just elements. It's just an element. It's just atoms bonded together as a molecule. It's molecular, but it's just atoms. They haven't got any charges at all. So the Cl minus goes from -1 oxidation state up to 0. If it goes up, it's been oxidized, so that's gone from oxidation state -1 up to oxidation state 0. Write a half equation for the reduction of chlorate 1 ions to chlorium. Well, first of all, you've got to know what chlorate 1 ions are. You've got to learn that. A chlorate ion is like a chloride ion, except it's got an O in there. So it's a Cl minus, but it's got an O in there. To form chlorine. Chlorine in acidic conditions, we'll worry about that in a minute. Chlorine we know is Cl2, so I've got 2 ClOs making Cl2. By the way, why is it chlorate 1? What's the 1 come from? Well, it refers to the oxidation state of the Cl. Oxygen is in group 6 of the periodic table. It's got 6 electrons in its outer shell. It wants to gain 2 electrons and form a 2- ion. So it has oxidation state -2, a 2- ion in there, except it's only got 1 minus left over, which means that this must be +1. +1 minus 2 leaves 1 minus left over. So the +1 refers to the oxidation state of the chlorine. The 1 means that the chlorine is in oxidation state +1. +1 minus 2 leaves -1. And we know oxygen is -2. It's always -2 because it's in group 6 of the periodic table and wants to gain 2 electrons, gain 2 minuses. The one problem that I've got here is now I've balanced the Cl's, but I haven't got any O's on the right hand side, and I've got a minus on the left and no minuses on the right. So what do we use? What's in our armoury? What's in our toolkit that we can use? If we've got O's that we can't balance, we can always add H2O. And if we can make H2O, we're going to need H2O on the right hand side because we've got O's on the left, so we're going to make O's on the right. Now when you make H2O's, you've got H's in there now. You can always use H pluses, not H's but H pluses. Acids provide H pluses. That's what acids do. They release or donate H pluses. So I can use H pluses and H2O's. I can always add that in. Let's have a look at that then. So that looks rather complicated now, but it's not really. Let's have a look what I've done. I've got O's on the left hand side. So I've made H2O on the right hand side. So I've got O's on the left and O's on the right. I said I could use H2O's to balance up the O's. I've got O's on the left hand side, I've got O's on the right hand side. I needed 2 ClO's to balance up with the Cl2. So I've got 2 O's on the left hand side, so I need 2 H2O's to balance up the O's. 2 O's, 2 O's. Now I've made 4 H's. I said I could use H pluses. So 4 H's, I'm going to need 4 H pluses. Now let's work out why I've added 2 minuses here. On the right hand side I haven't got anything with any charges. There's no charges on the right hand side, so I need no charges on the left hand side. 2 minuses, 4 pluses. 2 minus and 4 plus means 2 plus. So I need 2 minus to cancel out the 2 plus. Let's add up all the charges here. 2 minus, 4 plus, 2 minus, 4 minuses and 4 pluses. No charges on the left hand side, no charges on the right hand side. Write an overall equation for the redox. That's some reduction here and some oxidation. I've got to combine everything on the left of these equations and everything on the right of these equations and then simplify and cancel. So what have I got on the left of this equation? I've got 2Cl minus, and on this one I've got 2 ClO minus, 4 H pluses and 2 electrons. So I combine everything on the left of these two equations. 2 Cl minus on the left of this equation, 2 ClO minus on this one, 4 H pluses and 2 E minuses. So that goes on the left. On the right hand side I've made Cl2 and 2 electrons. That goes on the right. And on this one Cl2 and 2 H2O. So I combine all those. So everything on the left of these two equations goes on to the left of the overall, and everything on the right of these two equations combines and goes everything on the right. Now, can I simplify this a little bit? Let's have a look what I've just done. Okay, I've cancelled out the electrons, so I've got 2 electrons on the left and 2 electrons on the right. That's important when you balance 2 half equations, that the electrons cancel. The half equations have electrons in them, but the overall equation can't do. We may come to a more difficult question where if we don't have 2 electrons on the right and 2 electrons on the left and they're not going to cancel, we might have to multiply through by a number so that the electrons on each side cancel. But on this, in this case, it's quite a straightforward one because 2 electrons are made on the right hand side of this equation, 2 electrons on the left, so the left hand and the right hand cancel. The electrons cancel, and that's why I've cancelled them out here. I've also combined Cl2 and Cl2 to make 2Cl2. So I've just simplified it. Now notice I've got 2, 2, 4, 2, 2. I could divide through by 2 and make Cl minus, ClO minus, 2 H pluses, so I've divided the 4 by 2, Cl2 and 2H2O, so just divided by 2, and I've now got an overall equation. A solution of sodium chlorate 1 was added to a colourless solution of potassium iodide. So what I've got is I've got chlorate 1 just as before, but instead of chloride making chlorine, I've got potassium iodide making iodine. So what I've got this time is instead of chloride making chlorine, I've got potassium iodide making iodine. So iodine is a black solid, but when it's in solution, when there's liquid around, when there's some water around, when it dissolves, it goes to a brown colour. So it makes a brown colour because it dissolves. So the black solid of iodine dissolves to make a brown solution. It's iodine because I- is oxidized. So Cl- was oxidized to Cl2. So I'm just going to finish that off my third mark by saying I- is oxidized into I2. Remember what I was saying here about oxidation. Cl-, oxidation state -1 going to 0, -1 going up. -1 going up means that there's oxidation going on, or you could say it's lost electrons, but the I- would lose electrons, and instead of forming Cl2 would form I2. I2, as I say, is a black solid, but in solution it dissolves to go brown. Question 9. A student was given a powder made from a mixture of anhydrous, that just means dry barium chloride, and anhydrous dry magnesium chloride. The student dissolved. Every time I see barium chloride, I know what's coming. Barium chloride reacts with sulfuric acid to make barium sulfate, which is a white solid. So the test for barium chloride is sulfuric acid, or barium sulfate is the test for sulfuric acid or sulfates. So barium chloride reacts with anything with a sulfate, like sulfuric acid or any other sulfates, and makes barium sulfate as a white solid. It's actually used in barium meals. You'll take barium sulfate and swallow it so that they can photograph, or x-ray rather, your gut, so it sits in your gut as a solid which can be x-rayed then and appears on an x-ray plate, where so you can actually have a look and see if you've got any ailments, any illnesses. You can x-ray a soft tissue like your gut or your intestine by putting barium sulfate solid down there as a barium meal. Anyway, so barium chloride and anhydrous magnesium sulfate. The student dissolved 1.056 grams of this mixture in water and added sulfuric acid. Here we go, it's going to make barium sulfate. The white precipitate, the barium sulfate formed, was filtered off, washed and dried. The mass of the solid was 0.764. We'll probably make some magnesium sulfate as well, but magnesium sulfate is soluble. Identify the white precipitate, that's barium sulfate then, used in barium meals, and calculate the percentage by mass of the magnesium chloride in the powder. So I'm going to have to work out the mass of the barium sulfate in there and then subtract it from the total mass of the mixture and work out the magnesium chloride. Okay, let's have a look what I've got so far. So the student dissolved 1.056 grams of the powder, and I got a mass of solid was 0.764 grams. So the barium chloride and the sulfuric acid make barium sulfate. That's the white precipitate. That will get me 1 mark. So now I've got the mass of the white solid, which was 0.764. I can work out the MR of barium sulfate using a periodic table, 233.4. So moles of barium sulfate is the mass divided by the MR. I know the number of moles of barium sulfate. Where's the barium sulfate come from? It's come from the barium chloride. So the number of moles of barium chloride must be the same. I must have 0.003273 moles of barium chloride if it's made barium sulfate, 0.003273 moles. So I now know the number of moles of barium chloride. I know the MR of barium chloride because barium chloride is BaCl2. By the way, barium's in group 2, so it's 2+, the sulfate ions are 2-. 2+ barium, sulfate SO4, 2-. They cancel each other out, BaSO4, whereas barium chloride, Ba2+ for barium in group 2, loses 2 electrons. 2 electrons since outer shell loses those 2 and becomes 2+. Chlorides in group 7 gains 1 electron in group 7, Cl-. 2+ Cl-. I'm going to need 2 Cl- to balance up with the barium 2+, BaCl2. Its MR is 208.3. So now I've got the MR of the barium chloride, I've got the number of moles of barium chloride. Moles is mass divided by MR, so moles is 0.3273 is the mass divided by the MR, 208.3. So the mass of these two numbers multiplied together, 0.003273 times 0.208.3, 0.6818 grams, and now know the mass of the barium chloride in the mixture. Now the mixture had a mass of 1.056 grams. So I know the mass of the mixture, I know the mass of the barium chloride in there. If I take the total mass of the mixture, 1.056, and I subtract the mass of the barium chloride in there, 0.6818 grams, I end up with 0.3742. That's the remaining thing in the mixture, which is magnesium chloride. So I've got 0.3742 grams of magnesium chloride. I've worked out the mass of magnesium chloride. It wants me to do a percentage now. So I've got 0.3742 grams of magnesium chloride in a total mass in the mixture of 1.056. So I divide the smaller by the larger, multiply by 100%, 35.4%. Question 10. Which element is in the D block of the periodic table? So a D block element is sometimes called a transition element, and they appear in this block here in the middle. So you're looking for something in the middle here in this block. So you've got group 1, you've got group 2, then you've got group 3, 4, 5, 6, 7 and 8. You're looking in this block here. So something in this middle block, and something that's on the list here. Tantalum is here. Yep, so you could identify it in this middle block. Anything in the middle block is a D block element, sometimes known as a transition element. So your answer is C. Which species contain an element with an oxidation state of +4? Well, let's have a look. So oxygen is in -2 because it's in group 6 of the periodic table, gains 2 electrons, -2. So 2 minus 2 is a -4. So the nitrogen here is in +5, because +5 minus 4 leaves +1. So that's in +5, so it's not A. An element in oxidation state -4. So oxygens are in -2, as we've said. 3 minus 2 is a 6 minus. It's got a 1 minus left over, so the Cl is in +5. +5 minus 6 leaves -1, so it's not B. H2SO3. H is a +1s. The oxygens are -2s, so 3 minus 2s is -6, +1 +1. The sulphur is in +4, so +1 +1 +4 -6 to leave no charge left over. So the sulphur there is in +4. Let's just check this one then. PCl5, no charge. Cl is in group 7, so forms a 1 minus ion, -1 oxidation state. 5 1 minuses are 5 minuses from the Cl's. The phosphorus, the P is in +5. So your answer is C, with the sulphur in +4. Question 12. There are 392 moles of pure gold. So why have they given me moles of gold? Well, I could work out the MR of gold and work out from moles in MR, I could work out the mass of the gold. In a bar measuring 10 by 10 by 40, why have they given me a length and a width and a height, or 3 dimensions of a bar of gold? Clearly they want me to multiply height by width by length to work out the volume. So now I've got the mass of the gold, I've got the volume of the gold, and density is mass divided by volume, and I can work out the density. Right, let's have a look then. So the volume of the bar is 10 multiplied by 10 multiplied by 40. It's 4,000 centimetre cubed. Now here it says it wants in grams per kilograms per decimetre cubed. So to get centimetre cubed into decimetre cubed up into a larger unit value, I've got to divide by 1,000. 4,000 divided by 1,000 is 4 decimetre cubed. Looking on the periodic table, the MR of gold is 197. Moles is mass divided by MR. So moles is 392 moles. It tells me in the question is the mass divided by 197. So the mass of these two numbers multiplied together, 392 multiplied by 197, 77224 grams. Now it wants it in kilograms per decimetre cubed, so we've got to get this into kilograms. So to get grams into a larger unit value of kilograms, I divide by 1,000. 77224 divided by 1,000 is 77.224 kilograms. Density is mass divided by volume. So my mass is 77.224 divided by my volume of 4 decimetre cubed, 19.3. The answer is B. The ions of the two isotopes of iron are as follows. Which statement is correct? Well, first of all, isotopes have different numbers of electrons. They don't normally, but they've got different charges. So the charge refers to the number of electrons that have been lost, and so since they've got different charges, they've lost different numbers of electrons. The two Fe atoms, before they've become charged ions and lost electrons, did have the same number of electrons and the same number of protons. Different numbers of neutrons, because the mass number is different. That's what isotopes are. They've got different numbers of neutrons because and that's why the mass numbers change, but the number of protons and electrons are the same, unless they've become ions and lost electrons, and since they're two different charged ions, they've lost different numbers of electrons, and so the electrons aren't the same, and so the electronic configuration is not going to be the same. The ions both have isotopes containing 26 neutrons. No, they've got different mass numbers. That's what isotopes are. They've got different mass numbers because they've got different numbers of neutrons. Then the one has got fewer protons than the other. No, they've got the same number of protons. They've got different numbers of neutrons, hence different mass numbers. They've got different numbers of electrons because they've got different charges. They had the same number of electrons to start off with, but got different charges, so lost different numbers of electrons. But the number of protons has stayed the same. They're the same element, the same thing, Fe and Fe. They're both element Fe with the same proton number. So C is wrong. D must be right. After acceleration to the same kinetic energy, this ion moves more slowly than this one. Well, the heavier ion moves more slowly. That's the nature of it. The heavier it is, the more slowly it moves. So D is correct. Question 14. I've got successive ionization energies of an element X. Which one is element X? We'll have a look. The ionization energies go up. There's no surprise. We're losing electrons. We're keeping the same number of protons, so the nuclear charge is staying the same, but you're getting less and less electrons. So you're getting the same nuclear charge for less and less electrons, and that's why it requires more energy to remove subsequent electrons. However, we're getting a big jump between removing electron 3 and electron 4. Therefore, I suspect that it's in group 3 of the periodic table, and the first 3 electrons are from one shell, and the 4th electron is from the full stable shell underneath. So I think it's in group 3, and the 4th electron is from a stable shell underneath. It's in group 3. Which element's in group 3? Aluminium. Which of these decreases down group 2? First, ionization energy, so the energy to remove an electron. Yes, it will, because as the atoms get bigger and bigger and bigger, the nucleus is further from the outer electrons, so there's less nuclear attraction, so less energy is needed to remove that electron as the nucleus is further away. You also get more shielding as well as you get more shells, so A is definitely right. Let's just check. Decreases, no, atomic radius gets bigger, you get more and more shells. Number of protons, no, that gets bigger and bigger as you go down the periodic table. Reactivity with water, no, as you go down group 2, they get more and more reactive because they want to form 2+ ions, and those electrons are more easily removed if they're further away from the nucleus. They have a lower ionization energy, so they're more easily removed, so it forms ions more easily as you go down the periodic table and thus becomes more reactive. So your answer is definitely A. Question 16. Refer to the unbalanced equation when answering questions 16 and 17. In the balanced equation, the mole ratio for the sulfuric acid to water is. So what I've got to do is I've got to work out the numbers in front of the H2SO4 and the numbers in front of the water. And it'll either be 1, 4, 2, 1, 2, 4, 7 and 4, 9. Now you can put these numbers in 1 and 4 and work out whether it balances, but it's a bit of a long-winded way around it, because if I look on the left, this H2SO4 is the only reactant with S in it, and on the right hand side I can work out how many S's I've got, and I can work out what this number is. So I've got Cr2SO4 in brackets 3. There's one S inside the brackets. The atoms inside the brackets are multiplied by the number outside, so there's one S inside multiplied by 3. I've got 3 S's there. K2SO4, there's 2 K's and 4 O's, but there's 1 S. 3 S's and 1 S is 4. So I've got 4 S's on the right hand side, and here on the left hand side S only appears in here, and there's one S in there now, so there must be 4 in front of the H2SO4. So I've automatically got a 4 in front of the H2SO4. In the balance equation, the mole ratio for sulfuric acid to water, so I've got 4 sulfuric acid, so it must either be 4 to 7 or 4 to 9. It must either be C or D. So the question is, have I got 7 waters or I've got 9 waters? Well, now I've got 4 in front of here. I could work out, let's say, the H's. 3 2's are 6 H's, 4 2's are 8 H's, 6 add 8 is 14 H's. I've got 14 H's on the left hand side, now I've got 4 here. How many H's I've got on the left hand side? Oh, well, the H's only appear in the water, so I must have 7 2's of 14. It must be 4 to 7. What is the reducing agent in this reaction? Now, a reducing agent causes something else to be reduced. So if something else is being reduced, the reducing agent is oxidized. So when something is reduced, something else is oxidized, because reduction is gain of electrons, oil rig. Oxidation is loss, reduction is gain. So if something is being reduced and gained electrons, something's been oxidized to lose the electrons to give it to the thing that's been reduced and gaining electrons. So if something's been reduced, something's been oxidized, and the reducing agent causes something else to be reduced. It causes reduction, and in the process it is oxidized. So the question is, which of these are oxidized? So H plus is 1 plus oxidation state in there. What's it end up as? H2O. That's where it ends up. Oxygen's in group 6 of the periodic table, gains 2 electrons, 2 minus oxidation state. No charge left over, so that's minus 2. The H's must be plus 1 each. Plus 1 and plus 1 makes plus 2. Minus 2 for the oxygen leaves no charge left over. So the H plus is not being oxidized or reduced. Let's have a look what oxidation state the C is in C2O4 2 minus. Oxygen's minus 2, so 4 minus 2 is minus 8, so the oxygens combined give minus 8. There's 2 minus left over, so the 2 C's must be plus 6 together. Plus 6 minus 8 leaves minus 2 left over. So the 2 C's altogether are plus 6. They must both be in plus 3. Plus 3, plus 3, minus 2, minus 2, minus 2, minus 2 leaves 2 minus left over. The C is in plus 3. What does it become? It becomes CO2. So what is it in CO2? Well, oxygen's a minus 2, no charge left over. 2 minus 2 is a minus 4, no charge left over. The carbon is in plus 4. So it's gone from oxidation state plus 3 up to plus 4. If it goes up in an oxidation state, it's been oxidized. It's gone plus 3 up to plus 4. It's been oxidized. It will cause something else to be reduced. C2O4 2 minus is the reducing agent because it's being oxidized. It's causing something else to be reduced. Answer B. Question 18. Which substance exists as a macromolecule? So a macromolecule is a large molecule with many covalent bonds in it. Something like graphite or something like diamond. Quite strong with very many covalent bonds in there. What's copper? Well, copper's a metal. That's just got metallic bonds. It's got atoms that have lost electrons which are moving through the metal. They're delocalized, attracted by the plus ions that have lost electrons. So it's an attraction between the plus ions and the minus delocalized electrons. That's got metallic bonding in there. SiO2 is the main constituent of sand. Yes, it's got a high melting point. It's got many covalent bonds in there. It's in a tetrahedral structure. It's very similar to diamond. So your answer is B. P4O10 is molecular. It's got covalent bonds in it in a molecule. Quite a big molecule of P4O10, but that's it. It's a molecule of P4O10 with covalent bonds within that one molecule. The covalent bonds don't form a giant molecular lattice. MgO, well, magnesium's in group 2, oxygen's in group 6, so the magnesium donates its 2 electrons to the oxygen, and the Mg becomes 2 plus, the O becomes 2 minus. That's an ionic lattice. So with ionic bonding. So B is the answer. A pale brown mixture of NO2 and N2O4 is allowed to reach equilibrium according to this equation. When the plunger is pushed further into the syringe, the pressure increases and the mixture becomes paler in colour. So, what's happening here then? So as I increase the pressure by Le Chatelier's principle, it will try and lower the pressure. How can it lower the pressure? Well, it can lower the pressure by lowering the volume. So I've got 2 moles of gas on the left hand side and 1 mole of gas on the right hand side. So it can, if I increase the pressure by Le Chatelier's principle, it can lower the pressure by reducing the volume and turning 2 moles of gas down into 1. So this reaction here, or this condition here, the plunger increasing the pressure, the mixture becomes paler in colour, will shift the position of equilibrium to the right hand side and make more N2O4. So now we know that the N2O4 is pale and this is the brown gas. So N2O2 is a brown gas, N2O4 is a pale colour. So N2O4 is brown, N2O4 is brown, NO2 is brown, NO2 is brown. Yes, that's correct. This is brown, this is pale. NO2 is colourless. No, NO2 is colourless. So the answer is between A and B. So let's have a look next. When the syringe is placed in a hot oven, the mixture becomes darker in colour. So when I put in a hot oven, I'm making more of this dark NO2 and less of this colourless or very pale N2O4. So I'm making more NO2 when I put it into a hot oven, the equilibrium shifting to the left hand side. What does that tell me? Well, when I put in a hot oven by Le Chatelier's principle, it tries to oppose that change and lower the temperature in the oven. If it lowers the temperature in the oven, so it will lower the temperature by having an endothermic reaction, which takes in heat and lowers the temperature of the oven. So to the left hand side, because we know the equilibrium shifting to the left hand side, it's endothermic. So endothermic means that it will lower the temperature of the oven by Le Chatelier's principle, because the oven's hot, lower the temperature of the oven, oppose the change by Le Chatelier's principle, and it can do that because this reaction to the left is endothermic and it will become darker in colour because we know the NO2 is brown. So this way to the left is endothermic, so to the right it must be exothermic. So NO2 is brown and the forward reaction is exothermic. The answer is A. Question 22. 30 centimetres cubed of xenon and mixed with 20 centimetres cubed of fluorine. They react like this. 1 mole of xenon reacts with 1 mole of fluorine to make 1 mole of xenon difluoride XeF2. Now, for gases, volumes can are the same as, or can be treated the same as, moles. So let's say 30 centimetres cubed react with 20 centimetres cubed. 30 moles, you could say, react with 20 moles. That's not entirely true, but in terms of ratio it is. So we've got 30 moles of this reacting with 20 moles of that, or at least the ratio is the same. So I've got excess xenon and 20 centimetre cubed of fluorine, 20 of this. So 20 centimetre cubed of this would react with 20 centimetre cubed of that and leave 10 centimetre cubed left over. Now 1 mole of this reacts with 1 mole of this to make 1 mole of this. So 20 centimetre cubed of this would react with 20 centimetre cubed of this to make 20 centimetre cubed of this. I'm making 20 centimetre cubed of xenon F2. All of my 20 centimetre cubed of fluorine have reacted, so that's gone. 20 centimetre cubed out the xenon have gone, because 1 mole of this reacts with 1 mole of this, or 20 centimetre cubed of this reacts with 20 centimetre cubed of this, and I've got 10 moles of xenon left over. So I've got 10 centimetres cubed of this left over. I've made 20 centimetre cubed of this. 10 add 20 is 30 centimetre cubed. Which of the following solutions would react exactly with the solution containing 0.05 moles of sulphuric acid? Well, first of all, I've got to work out how many moles of each of these I've got. I've got centimetres cubed. I'm going to divide by 1,000 to get into decimetre cubed. And then what I've actually got is I've got concentration is moles divided by volume. So moles is concentration multiplied by volume. Once I've divided all these by 1,000 and multiplied by these numbers here, I've got concentration multiplied by the volume in decimetre cubed. I've worked out the number of moles of each of them. So the number of moles of A is 0.05, number of moles of B is 2, number of moles of C is 0.2, and number of moles of D is 0.05. So if it's reacting 1 to 1, 1 mole of this is reacting with 1 mole of this, then I'm looking for 0.05. 0.05 of barium sulfate, so this could be a possibility, or A is 0.05. So I could be looking at either A or D as a start. I need to know which one of these, barium hydroxide or potassium hydroxide, reacts in the ratio 1 mole of this to 1 mole of sulfuric acid. Well, I know that a sulfate ion made from sulfuric acid is SO4. It's 2-. A potassium is a 1+ ion because it's in group number 1. It loses 1 electron. So I'm going to need 2 1+ to balance the 2 minuses. So this K2SO4, 1 mole of sulfuric acid will react with 2 moles of KOH because I'm going to have to balance it with a 2 in front of the KOH. So this is going to react 1 mole of sulfuric acid to 2 KOH. So my answer isn't A. My answer might be D. Does 1 mole of barium hydroxide react with 1 mole of sulfuric acid? Well, barium's in group 2, going to form a 2+ ion. Sulfate, as we've said, is SO4 2-. So 1 Ba reacts with 1 SO4, so 1 BaOH 2 will react with 1 mole of sulfuric acid 1 to 1, so 0.05 moles of sulfuric acid will react with 0.05 moles of barium hydroxide, and we've discovered that D has got 0.05 moles of barium hydroxide to make barium sulfate. The answer is D. Question 24. In a car airbag, sodium azide NaN3, which is this, decomposes to form sodium metal, which is this, Na, and nitrogen gas, which is this. So 2 moles of sodium azide make 2 moles of sodium and 3 moles of nitrogen. The solid sodium metal then reacts with potassium nitrate. So 10 moles of sodium reacts with potassium nitrate to make 1 mole of nitrogen and some other products as well. If 2 moles of sodium azide react in this way, how many moles of nitrogen will be formed? Well, 2 moles of sodium azide, 2, would make 3 moles of nitrogen. So the answer, you'd think on first look, would be 3 moles of nitrogen. But in the process, it makes 2 moles of sodium. 10 moles of sodium makes 1 mole of nitrogen. So 2 moles of sodium would make 2 is a fifth, 0.2 of 10. So 10 would make 1. So 1 mole of sodium would make 0.1. 2 moles of sodium would make 0.2 moles of nitrogen. So the 2 moles of sodium actually make 0.2 moles of nitrogen. So I've got 3 moles of nitrogen. Add another 0.2 moles of nitrogen, I've got 3.2 moles of nitrogen. So it makes 3.2 moles of nitrogen. How many molecules of nitrogen will be formed? How many molecules are multiplied by the Avogadro's number? Because I've got 3.2 moles of nitrogen made. 1 mole of nitrogen has this number of particles, so 3.2 would have 3.2 multiplied by 6.022 times 10 to the power of 23, Avogadro's number, equals 1.93 times 10 to the power of 24. The answer is B.